Welcome to this explainer. Today, we're diving straight into the fascinating, honestly kind of messy, death throes of a star system. We're going to unpack one of the most structurally chaotic objects in our night sky and see how some recent mind-blowing breakthroughs have completely rewritten its history. Okay, so what actually happens when a dying star has, well, way too many companions? For the longest time, we looked at the remains of dying stars and thought, right, we understand how this works. But as we're going to see, when a star is crowded by a hidden family of companions, its end isn't just a quiet fade to black. It is an absolute cosmic demolition derby. To get a front row seat to this wreckage, we are taking a trip. We're traveling 2,000 light years away from Earth, straight into the heart of the Vela constellation.
And here is our subject, Caldwell 74. You might know it as the 8-burst or the Southern Ring Nebula. What we're looking at here is a chaotic, unbelievably beautiful, multipolar nebula. I mean, the dynamic range is just staggering, going from that intensely bright inner ring all the way out to the incredibly faint outer boundaries. It is gorgeous for sure, but to an astrophysicist, it's a massive, glaring anomaly.
Now, to really grasp the physics at play here, we need to quickly set our baseline. We're looking at a planetary nebula. Now, despite the historical name, it actually has absolutely nothing to do with planets. It's essentially the majestic, messy death shroud of a star. When intermediate-mass stars, much like our own sun, reach the end of their lives, they basically puff off their outer envelopes of gas, exposing this ultra-hot, dead core underneath.
Usually, the textbook structure of these nebulae is pretty straightforward. You've got a hot inner bubble, a dense shell or rim of ionized gas, and an outer halo. It's elegantly simple, right? A single dying star creates these nested, expanding shockwaves. The fast stellar wind pushes out, the gas piles up into a dense rim, and boom, you have a beautiful, symmetrical bubble.
But here's the catch. Caldwell 74 is definitely not a textbook case. When we deconstruct it, we find an ultra-out white dwarf burning at around 100,000 Kelvin right in the center. Around that, there's a bright elliptical inner ring, a mid-density outer ring, this really weird extended doily-like shell, and faint arc-like structures at the tips. Those faint arcs? They're huge red flags telling us this was not just a single star politely puffing off its outer layers.
This brings us to our next section, the hidden stellar quartet, solving a cosmic mystery.
For decades, the old models said this was just a simple visual binary system. We could see a bright companion star and a faint white dwarf, separated by a huge distance, taking over 25,000 years to orbit each other. But the James Webb Space Telescope data just completely rewrote that. The new reveal? We are actually looking at a dynamically unstable, hierarchical stellar quartet, or maybe even a quintet, that is actively driving the nebula's crazy shape. When we map this out with advanced instruments, we see things like intricate spiral structures and processing jets. You know, a single star, or even a basic binary system, literally cannot create this level of highly organized chaos. The shapes we're seeing here are the undeniable fingerprints of complex gravitational interference. So, what were the smoking guns? Well, the JWST gave us 3 major clues pointing directly to these hidden sculptors. First, a mid-infrared excess at the central white dwarf, basically signaling a warm, dusty disk and a super close, unseen companion star. Second, they found molecular hydrogen spirals in the halo, perfectly matching a low-mass companion orbiting slightly further out. And third, those faint arcs? Those are processing jets, launched by the chaotic wobbling of all these hidden stars. Which leads us to the next part, sculpting the cosmic dust, the mechanics of destruction. So, how did this all happen mechanically? It comes down to something called the eccentric Kozai-Lidov mechanism. Think of it like the ultimate catastrophic roommate situation. You've got this distant outer star, and its gravitational tug causes wild swings in the orbits of the inner stars. These tugs force the inner binary closer and closer until, bam, they merge. This triggers a common envelope ejection, violently blasting the host star's outer layers out into space. And because that central star suddenly lost so much of its mass, its gravitational grip weakened, and the outermost star's orbit dramatically expanded. The incredible thing is, if we map the velocity of that expanding gas, we can actually watch this 3D explosion unfold. By looking at these position velocity maps, we're not just staring at a flat, static picture. We're literally peeling back the nebula layer by layer to see the chaotic, 3-dimensional aftermath of that exact merger.
I think this quote from the researchers really hits the nail on the head. It perfectly summarizes the sheer violence of what went down. Those gorgeous, glowing rings and intricate doily-like structures of Caldwell 74, they are quite literally the wreckage of a dynamically unstable star system that tore itself to pieces. All right, moving to our final section, a new astronomical view looking at our own future.
You might be wondering, why does all this complex astrophysics matter to us down here on Earth? Well, it's absolutely crucial because planetary nebulae like this give us a preview of the final mass-losing phases for 90% of stars initially more massive than our Sun. So Caldwell 74 isn't just a pretty picture, it's a window into the distant future of our very own cosmic neighborhood. Which leaves us with this final provocative thought. If a single, well-studied nebula like Caldwell 74 can successfully hide an entire stellar quartet from us for decades, what other undiscovered complexities are just sitting out there in our own night sky waiting for us to look a little closer? Kind of makes you want to rethink everything you see up there, doesn't it? Thanks for joining me on this explainer, and keep looking up.